Before we proceed further, just to remind you, I would like to estimate this probability distribution. What does it mean? It means estimating the probability of something happening. In particular, for any possible choice of the terms appearing in this position, estimating what is the probability that this happens, right? At some point, we will have a specific document with specific values for these variables, and we want to estimate the probability, the a posteriori probability that this document would be generated from the probabilistic model we are considering, okay? So I always write this, where these are random variables, but remember that at some point we will have a document with specific values in these positions, and we want to know a posteriori what was the probability that this would happen given the underlying generative probabilistic model we are considering. Okay, just to be clear. Otherwise this way of writing doesn't make much sense. Good. So what shall we do at this point? We have seen that computing this, estimating this, requires probably the age of the universe in some sense. You would like to be able to generate, I don't know, the Holy Comedy at least twice to make a statistics, right? In principle, if you wait long enough, you will generate the Holy Comedy once again. But you need to wait very long time. We cannot afford this. So how can we proceed? We should try to simplify our lives. And a very easy way of simplifying one's lives is saying, let's assume that things are independent. So let's assume, for example, that the probability that some specific term appears in the first position is independent of the probability that some other term appears in the second position, and so on. Is this going to help us? Well, maybe. Okay. Of course, independence among the variables, the probability is the distribution is a conditioned one. Okay? It's always a probability distribution, only conditioned. Now, this is nicer, perhaps. So what is the problem with this? Let us now always think that eventually we want to be able to compute stuff. So let us assume that we want to estimate these probabilities. Now these probabilities are linked to some position, right? So for every position in the document, how would I estimate these probabilities? First of all, take all the document collection, consider the class C of documents, look up all the documents that have the same length n, and then check what is the probability that I will find a specific term in the ith position. You see here position is important still, right? Okay, for example, I mean this is, let me try to show you that this is actually sensible, it's not just hubris. So, for example, if you take the term I, subject, it is more likely to appear in the first position than in the third, for example. You see that? So, it is true that these probabilities, the distribution of these probabilities, they do depend on the position. Okay? And that's a problem. Because if we want to estimate them for every position, we have to estimate the probability of finding one specific term in that position, right? Okay? We already made a great simplification here. Why? By saying that the values taken by these variables are independent, essentially we are giving up something like syntax, for example. You can write, I go home. This sentence will have a certain probability of appearing in a document, but this sentence is much less likely to occur, right? By doing this simplification, actually we're giving them the same probability, essentially. I mean, not yet, actually not yet, because we still are sticking to positions. But essentially what we are saying is that what comes after I is independent of I. That's not true. For example, a verb is more likely is more likely to follow I than home, right? So we already gave up some syntax, some, not all of it, because still we still have positions. So in principle, we are accepting the fact that the distributions might depend on the position, which is likely to happen. But if we keep a dependence on position, then it means that for every position we have to estimate the probability of every possible term appearing in that position. It is still a huge search space. We cannot afford this. So what are we still doing? We are doing the following. For every term t, independence of position, independence among the variables, and independence of position. Now, these and these have the same probability. Okay? Oh, this is an oversimplification? Of course, it is. But we're interested whether or not it works in practice, right? And apparently in practice it seems to work. And this is not, if you think about, this is not completely strange, right? We have been using so far the bag-of-words model, the vector space. They are position independent, right? For every word, you just look the frequency or whether or not the word appears. And that already seems to give decent results. So it's not surprising that it is working, it is going to work in this case as well. Of course, it would work perfectly, much better if we were able to estimate these probabilities, but alas, we cannot. So we had to go with what we have, okay? So this independence of position, and then everything gets a lot easier. So at this point, why is this important? Because now to estimate these probabilities, it's a lot easier. We just need to see how frequently, for example, one term appears in documents of a given class. We don't care about the positions anymore. We just care how many times it appears in documents of the collection of class C, or the subset of class C documents. Okay? So, what are we interested? What is our first classification algorithm according to naive bias? Can I cancel a few things? Okay. Before you write an equal, you write this because you're hypothesizing this, not because it's true. Okay? So this is a model. This was some hidden truth. Okay, something like this exists perhaps. This is just our model. It is not yet completely specified, but we already have a model. Now, can we do something like this? Let's see what we want to have, which is going to be our algorithm, and then let's see what we have to estimate here, okay? Now, what is our classification algorithm going to be? Well, the first thing you may go for is something you have seen in machine learning, maximum likelihood estimator, right? So I want to assign this document to the class that maximizes this probability. Yeah, so this is the collection of all possible classes, the set of all possible classes of this quantity. So there is a nice thing about this formula, which is the following. So the argument, the class that is maximized in this expression is the same as this, because this does not depend on the classes, right? This is just the absolute probability of observing that document, nothing more. That's convenient. So I do not have to estimate this. So what I need to estimate now is this for every I, and this. I mean, this is something you have to do, but it is something you can do. Why? Because since these probabilities do not depend on the position, you see they're the same. So if I consider any term, t, I don't know, dog, the probability of observing dog given in any position, given that the document is of class C, is the same wherever dog appears. I'm not saying this is true. I'm just saying this is the assumption, the model we are considering. Okay? This is called the multinomial generative model. Okay? So it means that for every term, we can estimate this probability by looking at how frequently the term appears in documents of a given category. That's something we can do. I mean, we have to do this for every term, but we do it once and forever. I mean, how many terms have we got? 40,000 terms. Fine. For 40,000 times, I have to look in the training test the subset of documents of a given class C, and for each of them, I have to estimate the frequency with which the term appears. It will take long? Yes, perhaps. I'll do it on a cluster, but it's doable. It is something that I can do. This I can estimate. That's very simple to estimate. I mean, you have a training set collection, you just pick, supposing that the generative process is the following. First, I pick the class of the document according to this distribution that I do not know. I can estimate this with the fraction of documents in my training set that belong to that class. Right? It's a simple estimator. So things start looking nicer. Then we look for problems. Now we'll try to identify a couple of problems. So we solve them one at a time. Is everything clear so far? Okay, I keep on not using slides. I don't know why. But I don't know. But this is a summary of what I just wrote. Okay? Let's see if I omitted anything. Maximum a posteriori, because a posteriori stands for the fact that you want, given a document that was generated according to the unknown generative model, you want to, which we model actually in this way, you want to estimate the probability that that document was generated. Okay, you already observed the document a posteriori, and you want to know, yes, but what was the probability that this document would appear? A little bit like in a p-test, you know? You judge a posteriori what was the probability that then, let's say that that document would, that something would be generated from the null hypothesis. So, yeah, okay, this is what I was saying earlier, right? About estimating. Okay. Now that we have this very nice expression, let's try to see how we can estimate this stuff. So to use this model, we will need two things. I mean, we'll need for every class, we will need an estimate of this probability, and then for every term and every, I mean, this is a random variable, but I will have to estimate, which is when you estimating this means estimating the probability distribution, right? For every term. Yeah, that's exactly what we do. We are using the fact that for every position I, this distribution will be the same. Huh? Okay, that's a lot of simplification. I mean, that's the boundary between feasible and infeasible. Now, let's give notation. Let's say that you have a collection of n. When I say a collection, I mean a training set of n documents, out of which nc are of class C. Okay? What is your estimate of P? I put a hat because this is not a probability. This is a statistical probability. Okay, that's my estimate. Yeah? You do sampling. If your training set is large enough, you will have no overfitting, and you will estimate this rather accurately. There are theorems about this. Okay? Then, this means, what is the probability of observing term T in a collection of documents of class C in my training set? Let's try to figure this out. How are we going to estimate that? Okay, I have a document collections. I'm interested in dog. So, how would I use this document collection to estimate this probability for this class? Let's say that this is the class C of documents related to animals. So C will be the class animals. T will be the term dog. Case insensitive, of course. How do I estimate this from this? What do you think? Notice that when we took this, when we want to estimate the a posteriori probability for some document, if a word appears several times in the document, we want to estimate every term, okay? So if a term appears twice, we will take its probability twice, okay? Not once in this document, in this model. Because in this model, you are generating, how are you generating the document? After you have picked the category with probability P of C, and after you have decided the length of the document, you start generating the tokens that will form the document one at a time. And the same word can appear more than once, okay? This is very important to remember. It's different from the Bernoulli model, as we will see. So, how would I compute it? What is your estimate of this probability? Just to simplify stuff, of course you would do stemming, lemmatization, and so on. But let me do lemmatization for you, okay? What is your guess, or your educated guess? The question is, how frequent is the term in documents of the class with repetitions?
The number of all word in dog divided over the number of total word in the...
Great. So 4, I think, 1, 2, 3, 4, right? Divided what? 1, 2, 3, 4, 5, 6. These I don't think. 7, 8, 9, 10, 11, 12, 13, right? Am I correct? That's our estimate. Okay? Simple. Now the word has become a bit more orderly. Because, you see, there is a way of doing this, even efficiently. You know, your documents, they are a lot. Gigabytes of documents on a disk. Huh? How long do I need to take to estimate these probabilities for every term? You need counters. One counter for the term, and then in the denominator for every class, you need the total number of tokens appearing in the class. For every class, you compute this once and for all, right? You see that? Then, how do you compute this? You make a scan of the document on disk. But while you do the scan of the document, you are building a dictionary. For every term appearing in the document, whenever you find the term, you increase the value associated to the dictionary. So with one pass of your data, only one pass, so in linear time, you're going to compute both this number and all this probability. When you have finished scanning the file, all these values will be the right ones. I mean, the right estimations. Correct? Am I correct? Who is dubious? Was I too fast? Anyone who didn't get it? Now is the time to stop me. Okay? People, are you fine with this? Huh? Or you're in a third state? I don't know. Yes or no? Come on, if you feel unsafe, say no. Okay, you're safe. So I assume you got it. Okay? So at this point, we are able to understand, we are able to compute this. Because once we have computed all this, for the moment I'm not speaking of numerical difficulties or whatever. I'm just speaking of feasibility. So now in principle we can do this. We have our training set, we make this processing of the documents, we compute all these values, we compute these values for every class. At this point you give me a new document for every term the document contains, I will just look up the corresponding probabilities in my dictionary, I mean, estimated probabilities in my dictionary. I'll multiply them all, multiply a final time by C, which is not the same because I have several categories. So these, actually, if you look at the class which is maximizing this function, it also depends on C. So I have to multiply this at the end. I cannot say, yeah, this probability is the same for all documents. No, for a specific document, this is a constant factor, but it changes across classes, okay? And that's it. Then I will compute the max. Again, linear time in the length of the document I want to classify. And this does mean something feasible that you can do. And also, this is also, in a way, if your document collection, your training set changes with time, well, you have to update this stuff. But you can do it, right? For every term appearing, you look up your dictionary, you increase the number, you increase its frequency, and eventually you just add the length of the new document to the global counter for that class. That's okay. I mean, for every new document in the training set, which has been classified manually in the meantime. So it seems to be a robust way of proceeding. Which other problems do you see? What may go wrong? Just to stick number of documents of the given class, Cj, what I call C there. This is the number of documents. Sorry. This is the total number of times that this term appeared in documents of this class. Okay? I prefer to give you the intuition soon, because otherwise this notation may seem cumbersome the first time. Okay? But now I guess you know what I mean. What can go wrong here? Can you tell me? Remember, overfitting. What does overfitting mean? Overfitting in practice means that the algorithm, so how should I say, the classification function that you learn from the training set is not going to generalize, right? So I get a new document and I'm not able to classify it properly. So there is one basic case in which I'm not able to classify the document with this model. For example, if the document contains one term that is not appearing anywhere in the collection. It may happen, right? But still, the document belongs to the class. What is going to happen here? Well, the corresponding estimate of the probability will be 0. And there is nothing else I can do. I cannot boost it by increasing this probability. 0 is 0, always. What has happened? Well, that's a case of overfitting. My classifier will be very good at classifying, let's say, the same documents from the same training set. But what has happened is that I had not collected enough samples as to have at least one document containing every possible term that appears, that is associated to the class. You see what I mean? So, in some cases, it can just be a document that is a term that is very rare for documents in the of the class, very rare. Perhaps even a misspell. Okay? But sometimes the problem can be more serious. And it's not very easy to discriminate between, for example, having this fail, so giving me a 0 just because of a misspell in the document I'm examining, or giving me a 0 because I didn't consider enough documents in the training set. It's not very hard to tell what is the problem. How can I try to get rid of this? So let's say, have you any ideas about?
Add a term unknown. Add an extra term unknown that represents the word we don't see before. We haven't seen before.
Haven't not seen before. What do you do?
So you mentioned that there is a problem if we match an unknown word.
A word that appears in a document. I mean, what can happen is that you have a new document belonging to the class, but containing a word that was never encountered.
We set an extra feature represents the word we haven't matched.
Extra feature? What do you mean? So you mean that is a new term?
Yeah.
Yeah, but that's a document you still want to classify. You don't know that it belongs to a given class yet.
We can find a word that could be similar.
Okay, but yeah, you could do that. For example, canine and dog. You could try to say that canine is some way associated to dog, but that's extra work, and that perhaps is not what you want to do. You can try with some simple observation.
We can add one to the numerator.
Oh, you just, you put a 1 there, so you just forget about it. That's less stupid than it looks, actually. So, but 1 is a very big value, you know? These probabilities, if you compute them, they are 10 to the minus a lot. So, which is another potential problem, but we'll come to that. So what can you do? You can try to argue, you can try to make a following observation. Now, let's assume that my training set is large enough. What does it mean large enough? I don't know. It means that perhaps I actually was very unlucky. So I collected large enough samples. The theorems about VC dimension and sample size and so on, they don't tell you that you're exactly getting the correct distribution. They just tell you that your mistake, your error in your estimate is bounded. But of course, when you want to estimate the frequency of something that is, the probability of something that is very unlikely, the smaller the probability, the higher the number of samples you need. So there is always going to be something that is going to be left out, regardless of how, not regardless, but despite you having collected a sufficiently large sample. So what can you do in that case? You can do, for example, you can think like this. So yeah, I didn't get this term, but this term never showed up in my entire training set. Even if it were to show up, its associated probability should be very small. How can we account for this? We can do something.
Logarithm.
Well, logarithm of 0. Yeah, non-zero, right. We do something else. We say, you know what? How was I estimating this? With this. Let's try this formula again. Number of documents of class C that contain, sorry, I'm still making the same mistake. That's for Bernoulli model. Total number of times that token T, so the word T appears in document of class C, divided by what? Total number of tokens in documents of class C, right? So, okay, for every token, every possible token, I count the total number of occurrences in documents of this class, and then I get, that would be the 13, okay? This sum would give me 13 for this collection. Okay, some terms perhaps do not appear here. Okay, that's what I do. The problem is when this is 0. What can I do? I mean, what is the idea behind? If this is sufficiently larger than 1 to be relatively significant, I'm not doing that big of a mistake. If this is 0, it means that probably it is not much more than 1. If I expanded my training set collection, I wouldn't get a value much larger than 1. So I can, well, smooth it to reduce overfitting in this case. This is called Lagrangian smoothing. Okay, there is a reason for that. But if you do this, things are going to work. And still, a word that never appeared in the document collection is going to be penalized a lot anyway. Because here you are dividing by what? You are dividing by the total length, the total number of tokens in your document collection, plus the vocabulary size. Okay, you see that? So, this is something that is done in practice. Or you can, instead of using 1, you can use some alpha. Alpha can be something non-negative, of course, which you tune until you get the results that you like most. Okay? That is what is done in practice. So at this point, this product is never going to be 0. And you're okay. What else can go wrong? Let me see if we have got this. Yeah. That is the equivalent of this. We didn't see this. You can do more complicated stuff, but that will be enough for us for the moment. That's the one we have seen, with just a different notation. But I try to use the notation that you find on the book, okay? Which is your primary source of information. I repeat, not this. Very nicely made slides, but slides are not material for study, okay? They are just for me. Questions so far? No? Okay, we are almost there. Yeah, we are almost there. We slightly change the model, we see another model, and then we will finally see how we can really work with these in practice. Because we are not yet done. This is something we can compute for the moment. But what is going to happen is that probably you get zeros, all zeros. Not because they are 0, but because of rounding. Because you're running on a computer, and it's very easy to get 10 to the minus 9 here. Okay? That's a problem that cannot be neglected. So, let's try to see what is the idea behind. I was telling you, actually these models, so naive bias applied to text classification is deeply rooted in language generation models. Okay, so there has been a lot of research on generating, let's say, more or less well-formed sentences of human language. You know that, right? From, I mean, going from actually going back to context-free, context-sensitive grammars, you know, Chomsky, all this stuff, and probabilistic models. For example, there are models of generating human languages using hidden Markov models, so Markov chains. These are something in between. I mean, these are the simplest model you can think of, but there are more sophisticated ones. So the one we are looking at is called the multinomial generative model, and it is actually used because in practice it does a more than decent job. So what do you do in practice? Normally what you do is to compute frequencies of terms appearing in well-formed human sentences, and then you use those frequencies, which are estimate of probabilities of terms appearing in a given document, to generate synthetic documents. It is clear that if you use a document generation model like this, you will very often get perhaps the right frequency of words, but not the right order, right? That's clear. But that seems to be enough for text classification at a basic level, at least. For example, if you had a model like this, what is the probability of generating a sentence like this? according to this model, this would be your probability. That is why we are going to have rounding problems. Okay? If you think about it, it makes perfectly sense. There is no way that you're going to make these probabilities much bigger. Also because, if you remember, we decided that this was useless. Right? Actually, it is useless because for the maximization problem we want to solve, but it is very useful. It would be very useful to avoid rounding errors. Okay? But, I mean, even that is, now that I think about, even that is not obvious, because also here you would have rounding errors. Okay? So, you divide a rounding error by a rounding error, nothing good happens, I guess. If you consider, for example, two different models, you may have different a posteriori probabilities of generating the same sentence. Okay? Yeah, okay. These are some of the approximations we have been doing at some point. You can go over them again if you want. As I was saying, there are much more complicated models. I mean, it's a fascinating area of study, in my opinion. It's a really interesting area. Now, is there any other model I may have used here? Actually, yes. There is another model I may have used here. But now, in order to do this, you have to follow me. We are going to use the same type of expressions, but with a different meaning. So there is another model we may use, which is the following. It's called Multivariate Bernoulli model. You know already. You all know Multivariate Bernoulli model? Who doesn't know? Never heard of? No, it's just for my, okay. Don't have to be ashamed of. There is nothing to be ashamed of. So if you never had machine learning, for example, probably you don't know it. Who never heard of okay, Bernoulli? Okay, great. At least I have a few students that. Okay, let's try to go over this again. Remember, that is what we were trying to estimate, right? You remember, so we want to solve this. Our question is this. This is our question. I observe this document. What is the probability that it is of some class C? In order to compute this, we actually try to estimate the probability that I would observe this document, such a document, if this were the class according to which the document is generated, from which the document is generated, right? And then we have seen we were interested in this type of expression. Actually, we don't even need a product. I mean, we will use a product, but okay, this is the key quantity we have to compute. Now, of course, we don't know this quantity. We don't know which is the real quantity, so we find the model, and we try to fit the data to the model. In the model we found, we were assuming that every document is generated, for now, by simply generating, first deciding the class according to the hidden probability of C, then choosing the length of the document according to the distribution of the document lengths for documents of that class, which we can also infer from training set. And finally, once we have decided the length of the document, we generate the document one word at a time, considering the probability, this distribution, okay? So, this is one possible model, in which case each of these values, each of these variables will take a value, which is a different term from the vocabulary, but we can use a different model. For example, we can decide to have a more, how should I say, simplified representation of a document by a binary vector. So every document in this case is represented by a binary vector of length n, where n is the size of the vocabulary now. So now, the size of the vocabulary is n. Before, n was the length of the document, okay? So this is a more, it's a simpler way of representing documents in which every document is represented by a vector, a binary vector of the same length, n. So n is no longer some parameter that you have to generate a random variable. It's no longer a random variable. It is fixed, is equal to the size of the document. And then each variable is set to 1 or 0, depending on whether the corresponding term appears in the variable, in the document or not. So it is clear that in this case you're losing information. Because in the previous model you were generating a real document, you are generating, in this case, a representation of a document that only contains summary information about each term. It only tells you whether or not the term appears in the document or not. Okay? Can we do this like before? Yes, of course. We can make the same assumptions. Appearance or not of a document, of a term in the document is independent of appearances of other terms and also of the position, and we get the very same expression as before. Question mark meaning that this is only equal if we make these assumptions. Okay? I rewrite this like, instead of putting E ranging from 1 to n, which is correct, I put this just to emphasize that now this is no longer the number of words appearing in the document, but it is the vocabulary. It is the size of the vocabulary. And then I have this. Okay? So we are in the same situation as before. And again, we have to estimate these probabilities. Now, the probability of the class is estimated like before. How do I estimate these probabilities now? In particular, how do I estimate the probability that one term appears or not in the document? Tell me. Come on. I only have to say the term appears in the documents of class C or not. How do I do that? It's a binary information. So, again to this example. The probability that dogs appears in the documents of the collection, how much is it? How do I estimate this probability for dog? Now, this is not the same probability as before. I just want to know whether dog appears or not. I could write this as x, okay, where this is a Bernoulli variable. This is the meaning of this expression. So dog appears. What is how do you estimate the probability of the dog appears in the document collection from this document collection? What does this mean? Pick one document uniformly at random, right? And see whether or not dog appears. Appears, 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 doesn't appear. So 3 over 4. Right? That's my estimate. Actually, let's put an equal here, but a hat here, just to represent the fact that this is an estimate. It is not the real distribution. Okay? Otherwise, it is the same. It works the same as before. You will do the same. To decide classification, you will again run this classifier and so on. Again, processing the document collection will require, going over the entire document collection and so on. Very often what you do, at least for the first method, so for the multinomial model, when you have document of a given class, you just attach the text after one another and you create a super document. And you do the count for every term. Okay? That's all. The rest is essentially unchanged. The problems are unchanged, so if a term never appears, you have to do some smoothing. What do you think? How is this method going to work with respect to the other one? Is Bernoulli working better or less or worse than multinomial in practice? What do you expect?
It's not accounting for the repetition of single words. So
it's not accounting.
yeah,
It's just
so maybe it might be worse.
yeah. So if you have one term appearing once in a document or 10 times or 100 times in the document collection of a given class, you don't care. So this essentially brings to higher, how should I say, instability in the answers, okay? So in practice, the multinomial distribution seems to work better in practice. Of course, there are also variants of this model that fix a number of the problems. Okay? Whenever you get those strange things like a letter in between, that means the terms that appear in the middle. I don't know why there is an L pops up. Okay? That means point, dot, and so on. So, this is just summarizing the things we have already seen. I was perfectly in time today, almost. These are the things you have just seen, just with a slightly different notation, but So there is the last thing we should address, and for this I'm not going to use the blackboard. I'm tired, and it doesn't deserve using chalk. So this is the last thing we have. I'll go back to this, but before going back to the complexity, let's try to address the last issue if you want to have a practical implementation. If you want to have a practical implementation using this expression, eventually you will fail because of rounding errors. I mean, if you have a document with just 100 words and every probability is, I don't know, how large can it be? 0.05 perhaps? 0.05 to the 100, that's something your machine, even with 64 bits, pretty soon is unable to represent, so you get a nice 0, and your analysis is over. No classification, all this probability eventually are 0. How can you get around this? One way to sidestep this problem can be taking the log. I mean, the log is a monotonic increasing function, right? That's a very nice property. So if you take the log of this expression, what do you get? What do you get? Well, first of all, let's begin. Let's see if log makes sense. Of course, it makes because I'm going to apply it. But if I take the log of 10 to the minus 9, which I have trouble, so 10 to the minus 100 even, I get minus 100, which is a nice number that I will easily represent, right? So, then there is another nice feature. Here you have products. Products are nasty for real numbers representation. But a product in logarithmic language, jargon, becomes a sum. And we like sum. That's something our machines do very easily. Okay? So, forget about also the exponents that you have here if you have exponents, because perhaps two terms have the same probability, so you will get some exponents. The exponents are integer numbers. So the logs will be some real number, perhaps, a small real number probability multiplied by an integer. That's something we more or less are used to. And then you get this nice expression. That's what is actually used. Okay? You take your estimates, you take the logs, actually that is what you store in your memory, and whenever you need to do something, you just use the sum. And that's it. Nothing else. Okay? This is something you compute in real time, of course. All the rest is pre-computed on your test, on your training set collection. Final thing about complexity. Actually, we went over this before. But to do the training of the multinomial model, for example, first of all, you have two potential sources of complexity. The first is that you have to compute for every term, and there are, let's say, cardinality of V terms, right? For every term and every class, you have to compute this probability, right? Whichever model you're using. So, number of classes times number of terms. That is the second term appearing there. On the other hand, to estimate these probabilities, you have to go over the entire document collection, right? Your training set. So you have to consider the total, your cost is proportional to the total number of tokens you will find in your training test, right? D would be your data set, so the size of your data set, the number of documents, times the average length of a document, okay? If you want to write it in a nicer way, the sum of the lengths of the documents, which normally is larger than that, because you need a training set that is large enough. For example, you will need at least a document per term, for the reasons we were saying before. So very often, the first term is larger than the second one. So your cost is mostly dominated by the linear time of scanning your entire document collection once. There is more to say. Yeah, we can check this exercise next time. You can try to go over it. It's a bit boring. You have to do the hand calculations. Don't choose logs here, okay? Also because the maximizing class is the same, even if you don't choose logs, right? So you can just go for fractions. I have not the time to go over it now. We'll do next time. Is there anything else I was demanding? No. But today, I think we can stop here. I don't know who is going to show up next Thursday. If it is me, we'll finish this and perhaps start something else, I think. If it is the other big guy, I don't know, you may do something applied. We have not yet decided. Did you do something applied last time? Last Monday? Or last Thursday? Nope? Okay, then I think he wants to torture you with some code next time, I guess.